Hello everyone, today we discuss contest 15. Pretty nice results actually. Enslaves again solved all the problems, solved fused all problems except the last one in less than an hour, and then spent another 2 hours solving the last problem, but he managed to solve it. Good for you. Everybody else not solved the last problem, but last problem is tricky. I'll tell you it's not actually that difficult, but again, it's the hardest problem of the contest. It should be. Problem D is a little bit tricky. Okay, it's maybe surprisingly for me, but we will talk about why it was tricky and what problem you may have for about problem D. No, and that's it. Overall, pretty nice results. Let's go discuss the tasks. This time I recorded myself solving all the problems before, so let's just watch me solving all the problems. In the first problem, it's pure implementation. So you given some situation, you need to carefully implement what's written in the problem statement. What's written in the problem statement is actually we have two types of tables, we have two types of customers, we have groups of one, groups of two, and you need to carefully just simulate what's going on in the problem statement. Again, it's not that difficult, but it's actually not trivial as well. So some of my students managed to fail because they didn't read it carefully. So what's happening here may be a little bit unnatural for some of you. So we have groups of one, groups of two, and when we have a single customer, and if we don't have any single tables, we have only double tables. We take one of the empty two-seater tables and just assign it. And for some of my students, it was more natural to take one of the half-occupied tables. So for some two-person tables, I have only one customer. So when you have a second customer, it makes sense to put it in the same table because it will optimize the number of customers you may have in your cafe. But it's not what's happening here. So if I have empty table, even if I have two-seater tables and both of them occupied by a single person, I would do it instead. Yeah. So maybe a little bit more, maybe a little bit not logical as you expect, but that's what's written in the problem statement, and that's what you need to implement. Yeah. So sometimes the problem statement doesn't make much sense. So sometimes problem statement is very logical, very natural, makes all the sense. So you intuitively understand why you do what you do. Sometimes it's not. Sometimes they do some strange things in the problem statement. So always make sure you carefully read what's going on in the problem statement and just exactly implement what you need to be implemented. Yes, and here I make a bug. So here you need to count number of clients, not the number of groups. Yeah? So when you have group of two and you decline, you have two declined customers. But that's it. So this is problem A. Just careful implementation of the problem statement here. Let's go to problem B. So problem B is also mostly implementation, but it has much longer problem statement with a lot of formula and stuff. So it's hard to read, it's hard to understand what's going on. It doesn't have any pictures. So usually when you have problem statement like this, I would add some picture that explains what's going on. Because for some people, it's more natural to visualize. So to understand statement, if it is some visualized here. So if you add some picture, at least something, it will be easier for them to understand what's happening. But here they didn't add any picture. But again, what's happening in this problem, you can just read it multiple times and try to draw yourself some picture. That's what I would normally do. So what we have in this problem, we have sequence of cells, and we have the portals from these cells. In every cell, we have a portal to one of the cells to the right. So we have here, like you can see here, we have portal from cell I to cell I plus AI. So it's always go to the right. And what you need to do, we need to get from cell 1 to cell K. And since you only have one portal, you don't have any choice basically. So basically, this simulation problem. You just need to simulate what's going on here. And again, this is the whole program on the left. So let's see what I'm doing here. So I simulate program by maintaining my current position. So my position is X here. And every time I move, I use the portal, I move from position X to X plus A of X. Okay? So here I'm using the portal. And I stop in two situations. I stop if I reach position K, which is my destination, or if I reach the end of the array. So again, difficulty of the problem is to read the problem statement, understand what's going on. I believe this is the most difficult part of this problem. Implementation is kind of easy. You don't need to optimize anything. You just need to do what needs to be done. So you just simulate the process described in the problem statement and just check if it leads you to the destination. So if you reach the cell K, you output yes. If not, output no. That's it. So let's see. That's problem B basically. Let's go to problem C. Oh, problem C is fun. Problem C is fun actually. So what we do in problem C, we actually need to do something, and you don't need to minimize anything. So you need to reach the desired state with some sequence of actions, and you don't need to make this sequence minimal possible. Yeah. So what we have here, we have some number of wallets, and this numbers A is number of coins we need to put in every wallet. So for every wallet we need we know what number of coins we need to put in this wallet, and you just need to write a program basically. So you need to output the program that puts this amount of coins in every wallet, and you don't need to make this program short as possible, but you need to do at most million operations. Yeah. So you need to do this in at most million operations. And again, let's look at this. So we need to put these coins. So we need to put 300 points in 300 wallets. So in total, we spent 90,000 actions just putting these coins. Okay? So you need 90,000 times put the coin. And you have million operations. It means you need to spend at most 10 operations per coin. So for every coin you need to spend at most 10 operations. That's more than enough. Yeah. Yes, the trick of the problem is you cannot put two coins in a row. So after you put a coin, you need to wait at least one operation. So you're not allowed to make two put operations in a row. Yeah. So that's the trick of the problem. And what we can do, so if we don't want to make two put operations in a row, when we want to put something twice, let's just go somewhere. So we'll go right left or left right. Yeah. Yeah. So between every put operations, I will go left right, so I make sure I don't make two put operations in a row. And that's it. And if you do it like this, so for every put operations, you make this left right movement. So you spend 3 operations per coin. It's more than enough. So you can make up to 10 operations. So 3 is perfect. So my solution is very easy. My solution is not very optimal in terms of length of this program. So I will just greedily put these left and right operations until I'm done. It's actually okay. So when you see that the constraints are pretty soft, so you allow so then problem orders allow you to make more operations, and it's easier to program like this. Then just do it. Let's stop here. So this is the whole program. So what I'm doing here, before I put anything, so before I make this put operation here, I make this zigzag. So I go right left or left right. So I do right left if I'm not in the first. If I'm in the leftmost cell, so I go right left. For every other cell, I go left right. Doesn't matter actually. So it matters only for the first and the last cell. That's it. And this guarantees me that I don't put any two P operations in a row. So before any P operations, I have stuff like this. That's it. That's it. So again, the program that I create is not very short. Yeah. So you can do it much more optimal, I believe. So you can after every write operation. So if you have two wallets, you can go back and forth, and after every move, you put another coin. Yeah. So it will save you like half of these steps, but you don't need this actually. So when you see that problem can be solved easier, just try to solve it easier. So if your solution is easier, you have less bugs, you have less problems when you solve your solution. um, okay, so try to keep it simple. That's my advice for this problem. So uh, it's actually true even for harder, especially for harder problems. So this problem is pretty easy, so you can solve it anyway. But for harder problem, when you think like, okay, I need to implement my solution, it will take like, I don't know, 200 lines of code. Just stop and think at this point. Okay, can I do it easier? So if you cannot do it not in 200 lines of code, but in 100 lines of code, much better. Yeah. So you will save yourself a lot of time. You will save less time when you program it. When you will save a lot of time when you debug it, and so on. During the contest, it's always a trade-off. So if you spend more time thinking about implementing a short solution, you have less time actually implementing it, right? You can do it after the contest, for example. So if you during the contest you implement your solution, but you think it can be shorter, try to do it after the contest at least. So if you don't have time during the contest, do it after the contest. So look at your solution once again and try to simplify it as much as possible. So the next time you have similar problem, you will implement shorter solution, have less bugs, less problems. Okay, that's my advice. It's mostly advice for technical problems like this. When you have a lot of strange cases, a lot of steps, try to simplify it as much as possible. Problem D. Problem D is surprisingly hard. I didn't expect it to be that hard. So it's hard in several ways. So first of all, it's hard because you have this strange formula right in the middle of the problem statement. Looks scary. Yeah. So let's read this formula first. So what we have in this formula, we have some specifications of function, some definition function f, and definition function m. But if you look closer, actually, what function is defined here? So function f is basically sum on a segment. It's just written here. If you're not familiar with these mathematical symbols, okay, you need to you need to learn it. Sometimes it helps, like in these problems. So function f is just sum on a segment. Yeah, it's just very scary way to define the sum on a segment. Function m here is maximum of functions f for all segments here. So here, m is maximum of function f for all segments. Yeah, and function f is sum on a segment. So function m is just maximal sum on a segment. That's it. So m of a is the maximal sum on some segment of array a. That's it. They could write it just using words, but instead they decided to put some formulas here. It happens sometimes. Sometimes the problem authors think, okay, I know I know mathematical notation, so let's write the problem statement using just formulas. Happens. I'm not fond of it, but sometimes people do it like this. Try not to be scared. So try to kind of translate from mathematical symbols to some, just to words. So to try to find the meaning of these functions. Usually there is some meaning of the functions. Sometimes not. Sometimes people just write random formula and expect us to solve the problem anyways. But try to find at least some motivation for this formula. Yeah. So in this case, just some. Okay. It's easy. So when you think about, okay, I have a function of 3 parameters. But then you think, okay, it's just sum on a segment. Sum on a segment is something you can relate to. Yes, it's just sum on a segment. Easy. Yeah. And the same here. So it's just maximum of something. Okay. But then you think, okay, it's just segment with maximal sum. So not as scary anymore. So okay, so it's the first problem here is just to translate this problem statement from mathematical to what people actually use. Yeah. next. Even if you understand the problem statement, it's not that easy problem. So what we need to do, we can swap some indices. Yeah. So no, not indices. Swap some elements. They even write the code for swap here. Okay. Okay. So here, this operation is just swap two elements. Yeah. So what's the problem now? Now let's formulate the problem like normal people do. Yeah. So we have array. We can swap up to k elements, k pairs of elements. Yeah. So we can swap up to k pairs of elements, and we need to find the maximal value of the maximal segment. Yeah. So you perform some swaps, and then you should have a segment with maximal possible sum. Now it's a little bit less scary. So how to solve problem? Again, multiple ways to solve problem. I believe easiest way to solve the problem is like this. So let's look at this from another point. So what we need to do, we need to make segment with big sum. Yeah. So instead of thinking what swaps I make, let's think about this segment. So okay. Let's use black. So this is your array. So you perform some swaps. So you swap here, something swap, and then you have segment with a big sum. Some segment from L to R. Let's look at the problem from another perspective. Imagine I know this segment. So you fix this segment from L to R. So you know that in the end, this will be your maximal segment. Yeah. So let's try to maximize sum in this segment, not in some segment, but in this specific segment. Yeah. So how to maximize sum in this specific segment? Well, we need to swap some small elements in this segment with some big elements out of this segment. Yeah. So we take some small elements here. So imagine imagine it's sorted for simplicity. Yeah. So you take some small elements and replace them with some big elements here. So you take big elements from outside of the segment and swap them with small elements from inside of the segment. And you can swap up to k elements. So you take k big elements which are not in the segment and try to swap them to k small elements inside the segment. And after you do this, you find the maximal sum this segment may have. And you do it for every segment. How do we know the segment? Good question. We don't know which segment will be the maximal, but we can iterate all segments. So let's check all possible segments. There are like n square possible segments. And we can perform this check in like linear time. So you can find this k minimum, k maximums, okay, n log n, let's say. So if you sort everything, you can say n log n, doesn't matter. So in like n cube time, you can do it for every segment. So you can take every segment. For every segment, find this. Now let's look at constraints. So we have size of the array is up to 200. 200 is small enough. Yeah, so we can make n cube solution. It will work. So we will iterate. So let me finish the program. So what I will do here, I will iterate all segments. And for each segment, I will try to make the sum of the segment maximal possible. So what I will do here, I will consider segment from L to R. L inclusive, R not inclusive, like I normally think about segments. Yeah. So segment will consist all elements from L to R minus 1. This is one. This is why R starts from L plus 1 and including R and including N here. Now I will put all elements which are inside the segment to this vector in for simplicity. Okay, so this code is not very optimized, and I do it on purpose. Yes, so my task is not to make optimal code. My task is to make code that fits into time limit. Yeah. So what I will do, I will try to write the most clear code because problem is complicated. Yes. So I'll try to simplify my code as far as possible. So what I'm doing here, I take all elements which are inside the segment, put them in one vector. Take all elements out of the segment, put them in another vector. Yeah? Now what I will do, here I think a little what is the best way to do it. Here I will do it like this. Again, I try to do it in the simplest way possible. I just sort the array of all elements out of the segment. So I sort this vector out in decreasing order. And now I will take first few elements. So I will take the maximal elements. Yeah. So I take some first elements of my array and add them to my array in. So now, again, let's see. So now my array in contains all elements which are already in array in and these extra k elements, no, up to k. Now I will just take the maximal elements from the array in. Okay, let me show again what I've done. I did it too fast. So what I've done here. So I take all elements. Okay, let's stop here. So I take all elements inside my segment. Plus I take some big elements out of the segment, up to k elements. So I take k big elements out of my segment. Then I take all this stuff and sort it. Yeah. So I will take this in, will sort decrease in decreasing order. And now we'll drop last elements. I will take only these elements. If I do it like this, I don't care if I put these elements. So I don't care if I need these elements or not. So if these elements outside of the segment are small, and I don't need to swap them, I'll just keep them. So I take my segment, add another k elements, and then drop k smallest elements. Keep only these elements. And this is the maximal sum I can get. Okay, maybe it looks overcomplicated, but it is the easiest solution I actually found out. So I sorted in decreasing order and just calculate sum of the first R minus L elements. R minus L is just length of my segment. Here again, here on the left is my full solution, like this. Maybe not the clearest code, but it's the easiest solution that I come with. Okay, let's read your solutions. Actually, I'm actually interested in your ideas for this problem. It looks pretty similar. Yes, looks pretty similar. So we again put everything from outside. You optimized. You don't do. Okay, got it. Okay, so you do it, but still you have this for loop. So it's still n cube solution, but different. Nice. So I fixed the left border, put everything to the left to array A, okay, to array outside, and everything else to array outside. Okay. So you dynamically update this array outside. Why not? And I array inside. Okay, so these are the same arrays inside and outside, but you update them dynamically here. When you move border one position, you can update the arrays. Makes sense. But still you still sort them in the middle, so it doesn't matter that much. Okay. So this sorting works in n log n time. So you can just create this array on the screen. So time complexity is kind of the same. So both sides. Okay, so get greater into you get it like this. So you get it's another way to sort them decrease in order. Max. Okay, and here what we do, we try to we can swap up to k elements, but we don't know which elements to swap. So we swap some amount of elements and just update maximum. After every swap, we see if we get better result, we keep this swap. Another way of doing the same. Okay, quite similar. Got a very similar solution actually. I believe it's a little bit overcomplicated. So you don't need to dynamically maintain these arrays. You can just redo them every time. But yes, nice solution. Let's move next. Next problem E. About battleships. Battleships is a nice problem. There are multiple solutions. So what's happening? So okay, I didn't draw any picture. Let me draw a picture now. So what's happening here? I have again this sequence of cells, and I need to put a k battleships of size A. Yeah. In this array. So but then I have some moves, and the answer me it miss. So I miss some cells, miss here, miss here, miss here. And I need to find the first time when it's impossible to put k ships of size A. No, how to check if it is possible to put k ships of size k? No. For example, you can. Well, how would you check? So how to put the maximal possible number of ships in the current situation? No, you just go from left to right and put them greedily. So you try to put this ship in left. So you put ship here, put the ship here, put the ship here, put the ship here. So go from left to right and put all the ships. Yeah? And then count how many ships you have. If you have less than k ships, then it's impossible to put k ships. Again, if you just need to check the single situation, you can do it just greedily. Go from left to right, put the ships in leftmost possible position, and just count how many ships you can put. Now, how to update this dynamically? No, you can do it like this. So you can maintain these segments between misses. So you have these segments. For every segment, it's easy to count how many ships you can put. It's like length of the segment divided by a, no, plus minus 1. Because you cannot put two ships in the same, so they cannot touch each other. So you need to put at least one empty cell between two ships. So it's like length of this segment divided by a plus 1, plus minus, something like this. Yeah. So you can maintain these segments and just update the structure when you have new move. So again, when you have new move, so imagine you have some segments. Then you have a new move here. So this move is inside some segment. Okay. So you need to find this segment, remove it, and add two new segments here and here. Please don't draw. Okay. You can maintain like segments in set, for example. So you maintain them sorted by the left border, let's say. Okay. So when you have a new move, you find the segment with closest left border. So you find this segment, remove it from your set, add these two new segments to the set, and recalculate number of ships. So it's possible to do it like this, but you need data structure, you need sets, you need, okay, if you're familiar with sets, so you need set, and here you find lower bound in the set. Lower bound in the set can be found in log n time. So if you know how to do it, it's fine. It's fine. Totally possible. But it's actually can be solved much easier, I would say. How to find this solution? How to find the solution? I want to show you. You find it like this. So imagine what's happening in this problem. You have some state, basically. So initially you have a good state. Let's say good state. And then you worsen the state. So you make some bad changes for this state. So you add these bad spots. So you make it worse. At some point, your state became a bad state. So you have good, and then it started to be bad. And after it's bad, it's always bad. Yeah? You have a situation like this. You have normal state when you can put, so you can put k ships. And here you have bad state, you can't put. And your question is to find this position. And when you have a situation like this, you can use binary search to find this position. Yeah. Again, binary search works when you have some monotonical structure like this. So you have yes, then no. So you find this position when you switch from yes to no. If you can check for the state if it is good or bad, then you can find the place when you switch from good to bad in log n time by doing binary search. And that's what I'm doing here. So let's go back. So I will do binary search here. I will read. Okay. Okay. Now I'm doing binary search. Again, I have a special lecture about binary search and code forces. If you don't know how to do binary search, let me show you once again. Pom, 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 pom. So you can go to code forces. Here you have edu. Here you have ITMO Academy. And here we have binary search. Highly recommend. I explain very in all details how to do binary search, and we discuss a lot of tasks about binary search. So if you're not confident you can implement binary search in 5 minutes, just go here. Perfect lecture. Again, and a good and a lot of nice practical tasks as well. So again, so what I'm doing here, I'm writing normal binary search. So these are L and R are 2 pointers. L is pointer to something good, R is pointer to something bad. So if I do 0 operations, my point is good. If I do m plus 1 operation, my point is bad. Yeah. Because I don't have m plus 1 operations. Yeah. And here now it's in the middle. I have you need something intellectual. You need to check if the point is good or bad. And the way I will do it is like this. I will just create this array Z of and mark all my moves. So mark all my misses here. See? And then I will go from left to right and greedily put all the ships. Okay, maybe this code is overcomplicated. So I go from left to right. C is the number of cells I saw before. So if I saw A cells here, yeah. So I saw A empty cells. I immediately put a ship in this position S. Okay, here I make I++. Don't do it usually. It's not very okay. It's not very nice code style to change the variable which is on your loop. So this loop by variable I, and here I do I++. Not very clean, but it works. The way I do it, because I need to have one extra cell after the ship. Yeah. So after you have the ship, you need to skip one cell before you can put the next ship. So again, I go from left to right and count how many cells I have. When I have 8 cells in a row, I put a ship and move next. And here, and then I calculate. I check if I have enough ships. So I have at least k ships. If S is at least k, then I move the left border. Left border always point to something good. Okay? So if I have k ships, my state is good. Okay? If I have less than k ships, my step is bad. So I put if my state is good, I put left pointer here. If my state is better, I put right pointer here. That's it. And then I just output the result. Here I will make a mistake, but we'll fix it later. Yeah, here you need to output not M but R. Yes, that's why I output 5 and think a lot about Y5. Okay, it's a little bit embarrassing. No, but I will show you how I actually debug programs like this. So when you're not sure why you have wrong result, I usually just output everything. So I can look at what happened in my program. So if you just output one number in the end, it's kind of hard to get why this number is wrong. So I will output more numbers. So I will output my array Z. I output, let's see. So I output array Z. So I output number M, number S. So here I see. So my first binary search put in position 3. So I put this 3 once in this array Z. Yes, here see. I see that I can put 2 ships, one in the left here, one in the right. Looks okay. Then I think, okay, I need to put 2 ships. I can put 2 ships, but I need to put 3. Yeah. So this position must be bad. So I need to put right pointers. And I see that actually, yes, I will put right pointers here. But then I think why I output 5. So this all looks okay. Yeah, this part looks okay. But I output 5 for some reason. Yeah. So now I know where to look. Yeah. Because I know here something, what's happening here looks fine, but in the end I output wrong number. So I check which number I actually output. Okay, I check. No, I didn't check. I go, oh, look down there. Okay, it's actually okay. It happens actually much more often than you think. So it probably happened to you multiple times. So the bug is not always in the very in the place you will be looking for the bug. So sometimes bug is very strange place in the input, in the output, in some line which you write every time. So it's like when you read the array and you make bug when you read the array, you may do bugs everywhere. So it's and when you have bug in some inconvenient place like this, it's sometimes it's hard to find because you don't expect bug to be there. But again, that's how you debug. When you looked bug in all the convenient places, so in all normal places when you will bug, try to extend your search. Look at the places where else you can make have problem like here. So again I find out that I calculate everything right, but for some reason I output wrong number. So in the end I looked at the place when I output number and think, okay, maybe my calculation is okay, but my output is wrong. So I check there. Okay, I could do it faster, but okay, at least I did it. That's it. So that's problem E. Mm, Again, you can do it using data structures. You can solve it using data structures. You can solve it using binary search like I did. Up to you. Okay. Let's move to problem F. Now we have three problems. We have F, G, and H. I copied them from contest called Helvetic contest. So in this contest, you have for each problem, you don't have a single problem, but you have group of problems of usually three problems: easy, medium, and hard. So I just took all three of the problems because they kind of the statement reference each other. So if the first problem the first problem introduces you the zombie brains. So the zombie brain is what is zombie brain explained in this problem statement. And again, if you read it carefully, zombie statement is basically is a tree. So it is a graph which is a tree. So and the question of the first problem is just to check if the given graph is a tree. No, multiple ways again to check if graph is a tree. Easiest way is to check two things. You need to check if the number of edges is n-1, like I do here. So if number of edges is not n-1, it is not a tree. And then you need to check that the graph is connected. You can do it using DFS like I do, or you can do it using like disjoint union find. Yeah. So up to you. So any algorithm will work. So okay, it's not very hard task to check if graph is connected or not. Just find the best way. So find the way that you like the most. I will implement DFS. Okay, so I first use DFS and then I will implement it. So my DFS will just mark all reachable nodes. So I will call DFS from node 0 and it will mark everything reachable from this node. So I make this array Z. It will be an array of marks. Initially, all marks will be false, but then I call DFS from, okay, I can spell DFS, DFS from node 0, and it will recursively mark everything reachable. Okay, very simple implementation of DFS. Nothing to tell. So that's how we implement DFS. Okay, one of the shortest implementations of DFS actually. That's it. So I call DFS from node 0 and then check if all the nodes are marked. If I have, stop here. Okay, so if I have any unmarked node here, yeah, I output no. So this first out of these three problems about trees. Both other problems will be also about trees, like you would expect. So let's go to the medium problem. So in the medium problem, you actually have a tree. So they guarantee that the given graph is a tree, and you need to find the two nodes with maximal distance. So for the trees, it calls it diameter. Oh, it's for graphs also. It's called the diameter of the graph. So you need to find two farthest node in the graph. And for the tree, it actually can be solved using very nice algorithm. So again, there are multiple ways to find the diameter of the tree. For different situations, one or another way may be more preferable. I usually do it like this. So if I just need to find diameter of the graph or of the tree, yeah, only this and nothing else, I usually do it like this. So very simple algorithm. Well, let me stop actually. Magical algorithm. So how you do diameter of the tree? You start from any node. I start from node 0. Find the node with maximal distance from node 0. So you, from node 0 you find the node with which is farthest away from node 0. And then from this node you again find the farthest node. So, here. And this distance, second time you find the farthest node, you find the diameter. Magic. It's true because because how the distances in the tree works. If you take the fact is, I will not prove it, but no, it's easy to prove. Let's you have an success. Imagine you have a tree, and you have a diameter of this tree. So you have this diameter, and you have something else. What can happen with something else? So you have some middle nodes here. So since this is the maximal distance, so from this point you can't go farther than one element. Yes, from this point you can go up to two elements. Yeah, if you go more than two elements, even more than two edges here, like if you have three edges, then this distance will be more than this distance. So this is not diameter anymore. Yeah. So if we agree this xy is diameter, yes, then you cannot have more than two edges here, and here you can have up to three edges, and so on, and so on, and the same on this side. And okay, let's keep only up part. Now, if you take any node of the graph, like take this node V, and look at the farthest node from this node. If you find the farthest node, it will be either node X or node Y. Yeah. So from any node of the graph, the node with maximal distance will be one of these ends of diameter. So this is how diameters work in trees. That's it. So that's how it works. So this is why my algorithm works. So if I start from any node, take any node, find the farthest node. It will be one of the ends of diameter. Then you find the farthest node from this node. It will be another end of diameter. Now you find the diameter. That's it. So that's what I will do. I will call DFS twice, and yes, I will update my DFS so it finds the distances. Usually you find distances using BFS, breadth first search. Yeah, but for trees it doesn't matter. In the tree you only have a single path, so the distance is just not the shortest path. It's just length of the path. It's only one path, so it is shortest path. Yeah? So you can use a DFS, you can use BFS, anything actually will work. You can just you can do some dynamic programming over it as well. So here my array D will have distances. So I call DFS. Okay, I actually rewrite the DFS. I didn't tell you. Okay, I'll show you. So I rewrite the DFS for the tree variant. So my new DFS, this will is DFS which works specifically for trees. Let me stop here. So normally DFS uses marks. Yeah, so you make marks for the visited nodes, and if you visit node second time, you see it's already marked, so you don't visit it second time. Yeah, but if you have tree, you can do it easier. So you don't have marks, you only maintain the parent. This argument p is the parent of the node x, and so when you enter the node, you need to visit all its neighbors except the parent. Yes, because parent is already visited, you go from the parent. Yeah? It only works on the trees. So you can do it like this. So I don't maintain any marks. I just put this parent as an argument to my DFS. Okay, and here I think I also need to calculate distances. So here how I calculate distances. That's it. That's it. So I calculated distances from node 0 and find node x with maximal distance here. And now I will again call DFS from node x, calculate distances from node x, and find node y with maximal distance. Now this dy will be my diameter. Come on. So that's basically it. So that's the whole program. So I believe you can simplify it. Normally, I would actually find this maximum inside my DFS. So my DFS will return the maximal distance as well. Here I didn't do it, but okay, just sometimes I simplify my DFS even more. So you can write DFS, which calculate distances and returns the node with maximal distance. So you don't need to do this for loop. Okay, I'll leave it to you. So you can simplify this code even more if you like. Now, final problem. For the final problem, you actually it looks much scarier than the previous problems. What you need to do all the same things. You need to calculate the diameter of the graph, but your tree is changing. So you have changes of it. So you have multiple moves. In every move, you add one more node to your tree, and you need after every change recalculate the diameter of the tree. Looks scary, yes. Recalculating so again, you cannot just do all the same things. Yeah, so you need to change a lot. Okay, let me stop here. So let me tell you what I'm actually implementing, because I will do it really fast. So plan. So there are a few difficulties in this problem. First difficulty is that my graph is my tree is changing. Yeah, so the tree is changing, so you kind of need to recalculate it after every change. Looks scary. Another thing is you find a diameter. How do you update the diameter when you do the change? Thing is, diameter doesn't change that much if you make small change. So you have a tree. You have some tree. This is tree. Doesn't look like a tree, but it is a tree. This. In this tree, you have some diameter. Let's say x, y. So this is the longest path in my tree. If you add one more node, so you add this to my node, let's say v, and you add it somewhere to your tree, your diameter cannot change very much. So it cannot change by only one, actually. So your new diameter, yeah. So if your diameter changes, it means your new node is the end of this diameter. So now, if my new node is the end of the diameter, where is the another end of the diameter? No, another end of diameter is the farthest node from node V. Yeah. If you know one end of diameter, the another end will be just the farthest node from me. Yeah. So now, if this V is the end of my diameter, all I need to do is to find the farthest node from V in my tree. But, like we discussed before, the farthest node is the end of diameter. So the farthest node will be one of these nodes, X or Y. So when you add node V here, yeah, like this. So all you need to check. So your diameter is one of these three things. It's either XY or XV or YV. So one of these three things is your new diameter. So your diameter may stay the same, or your node V is the new end of the diameter. If it is end of the diameter, another end is one of the X or Y. So you just need to check these three things and find maximum of them. And maximum of these three things will be your new diameter. So what I will do, I will keep my current diameter. Not only the value, but the ends of this diameter as well. So I will maintain two ends of my diameter, current diameter. When I add new node, I will check if this distance is greater than my current diameter. I will update my diameter. To do this, the only thing you need to be able is to calculate distances in a tree. So I need to check, like the distance between V and X, is it greater than my distance from X to Y? Yeah. If it is greater, then I update my diameter, and the same from V to Y. Yeah, the same. Okay, now we simplify the problem. Yes. So before we needed to calculate diameters and stuff. Now we just calculate distances. See? So we kind of reduced our problem to just problem of calculating distances in a tree. So calculating distances in a tree is not hard actually. So how you calculate normally distances in a tree? You root a tree in some points. So you have a rooted tree. Now, when you have some nodes, let's say V and U, so you calculate the distance like this. So you go up, 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 then down, down, down. So you need to find this point. Then you find, so every path in a tree works like this. I go upwards and then go downwards. And you can easily calculate both these distances if you know this point. So if you know this position, you can pre-calculate the depths of all nodes like before, like we calculate distances. And then the length of this part will be just difference of these two depths, and length of this difference of these two depths. And this node is just LCA of these two V and U. Okay, LCA is very known task. So if you don't know how to calculate LCA in the tree, no, I will show you, but you probably need to watch another lecture of LCA. Not very hard algorithm. Maybe the scary part of this problem is that my graph changes. So your tree changes and you think, okay, I need to recalculate everything when I calculate LCA. You actually not, because your tree only expands. So you can after you add another node, here distances here are the same. So you don't need to recalculate everything. You can just build the final graph. So you add all the nodes from before your final graph. Then calculate everything you need for LCA for this big tree. Already final when you added all the nodes to this tree. Yeah. Now you go when you go backwards, you keep all the distances are the same. Yeah? So when you add new nodes, your distances do not change. So you can first add all the nodes, then for this big tree calculate distances, and these distances will be the same for small trees as well. Okay, hope's clear now. Let's go to my implementation. And implementation is actually not that difficult. What I'm doing here. Here I just read the data and build the graph. Yeah, yes, I do it like this. Why not? So here I just build in the graph. GPM calculate. Now my DFS will calculate distances. and also it will calculate the parser. So I will calculate LCA by using binary climbing method. Okay, there are multiple ways to calculate LCA. Binary climbing is easiest to implement. It's probably not the fastest in terms of asymptotics, at least. So it will use n log n memory. It will work in n time in log n per operation, but it's fine. So it's probably not the fast algorithm, but it will be fast enough. Yeah. So I will spend n log n memory. I will spend log n per request. It should be fine. 200,000. What can go wrong? Nothing can go wrong. 200,000 for n log n is. So now let me show you how I implement binary climbing. I usually implement binary climbing like this. I make a constant number of layers of binary climbing. Here I use constant max equal to 20. See? So I will use 20 layers of binary climbing. So my jumps will have lengths from 1 to 2 power 19. So my last jump will be of like 500,000. It's more than enough. You can put 18 here. It will also work. Yeah. I just always put 20 because why not? Yes, you don't need to think here. Yes, I always put 20. At some point, I found the problem when you have 2 millions here, so I need to put 21. Yeah, also happens. Uh, Here in my DFS, I will change my DFS in the following way. I will in my DFS, I will calculate distances and also calculate the parents, because for binary climbing you need to initiate the first layer of binary climbing. So you have jumps of size 1. Jump of size 1 is just your parent. So here I will say that jump of size 1 from node y is x. So my DFS calculates distances and calculates the first layer of binary climbing. And then I will just I will just calculate all other layers. So I'll calculate, so layer 0 is initiated in DFS. Now all layers from 1 are calculated here. Okay, let's keep it. It's just default binary climbing, boring. So that's it. So this is the whole code of binary climbing. It's actually very short, and it's nothing can go wrong here. Now I will actually implement it. I still need to implement LCA and dist, but I will do it later. Here I will just implement the algorithm. So I will implement what I need to do, and then implement these functions in the end. So what I'm doing, I maintain my current diameter. So my diameter is from node x to node y, and res is actually the value of this diameter. Yes. I believe I could start by a single node and have diameter of size 0. But I decided diameter of size 0 looks strange, so I'll start from 1. Actually not. You can start from diameter 0 from one node. It just looks unnatural, so I decided I would do it. Now I add nodes one by one again, like I explained to you. So I have node I. So I calculate distance from node I to x. If it is greater than my current diameter, I update my diameter. Here I decided I don't need to call it twice. Actually, it would be fine to call it twice. And then my diameter is from I to x. So I need to replace y with I. Yeah. So it was xy, and now it's x and I. Now I do the same for y. That's it. That's it. So this is the whole algorithm basically. Looks not that scary, see? So I will add some. Okay, so you have some actually code for these binary climbings and then for LCA and stuff, but this is the whole logic of the algorithm. So this is the intellectual code. Everything else is just technical. Okay, now I implement distances. So I find this like this. I find the LCA again. I will implement it later, but I know it's LCA, and just return this. So you take so d of x is the depth of the node. It's distance from the root. So it's distance to x plus distance to y minus twice distance from LCA. And now LCA again. LCA is very classical algorithm using binary climbing. If you didn't implement it before, again, try it. It's not the hardest algorithm. I usually implement it multiple ways to implement it. I implement it like this because it's easier to implement like this. So I just do all the jumps while I can. So if I can make a jump, so I go from all length of the jumps from highest from longest to shortest, and every time if I can make jump, I make it. So I kind of move as far up as possible, and then I will reach the LCA. So here first, here the first loop makes the depth of x and y the same. So if x is below y, I move to the same depth as y. Now x and y are on the same depth. If x equals y, then I return x. That means I'm in the same point. If not, then I move them as far upwards as possible. As soon as they are different. So I make all the jumps, but I make sure that x and y stay on the same level and they're different. So in the end, I move them as far possible up so they're different, so their parent is the same. So I just output the parent of one of them, x or y, doesn't matter. That's it. Okay, here I forgot to initiate some array d. Okay. And that's it. It like worked from the first try almost. Okay, not that scary problem actually. So again, it can solution consists of several steps. I believe that the most intellectual step is actually all this thinking about so just finding out how this diameter works in tree. If you didn't do it before, that may be new for you. But again, after solving few problems about tree diameters, it all starting to make sense. Yeah. So you kind of have this intuition how the tree diameters work in general, and then it's not a problem. So after you learn how the tree diameters work, the rest is kind of technical. So you know that the tree diameter should be something like this. So to find the tree diameters, you need to keep track of the distances in the tree. So you need to find the way to find distances in the tree, and you can find distances in the tree by using something like this. So you need to find LCAs, and you can do it using binary climbing, for example. That's it. So this is the last problem for this contest. Hope it was fun enough for you. Okay. So let's actually try to read some of your solutions. Let's check a solution for the last problem. I'm quite interested what you have here. Okay, you have LCA like normal. Let's say так. Looks a little bit overcomplicated. Okay. I'm not sure what's happening here. Here I believe we're finding the diameter by maintaining two maximums. Okay, but how you recalculate it? What? What? I'm not sure what's happening here. It looks overcomplicated. Mm. Hoo, 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 hoo. Is it some kind of two pointers method? What? So we have for u for starting from k. K is initially 1, but then we move it. And we have some b. Is it some square root decomposition? What happened? Maybe it is square root decomposition. Okay, good for you solving this problem actually, using this method. Yes, I believe it can be solved using square root decomposition. So you split all the requests by blocks of b. Okay, makes sense. So after every b new element, you recalculate the whole dynamic programming. And in the middle, you either have this diameter or one of the new nodes, and you have up to square root of n new nodes. So you can check. Okay, makes sense. Yeah. So you take your new node. You use your new node. You check previous previous block. You check if this is a diameter from these two nodes. If not, it must be diameter of this. So you calculate the previous diameter using this nice dynamic programming. And this dynamic programming, you check for two maximums. For every subtree, you find two maximums, and okay, then you take maximum of sum of these two maximums over the whole tree. It will be your diameter. Okay, got it. Good for you making this solution to pass all tests. It actually takes a lot of courage to write something like this. Good. Again, it's not. So you try to find this simple solution. But if you didn't try the simple solution, you find hard solution. But you manage to implement it and get it accepted. Good for you. Do it. So again, after you learn after you get some skill of implementing stuff like this, you actually get better at implementing harder algorithms. So if you manage to implement this, you will be able to implement harder algorithms. When you have harder problems, you have more skill to implement it. Good. So that's it. That's the contest 15. Thank you for coming. See you next week.